Welcome everybody, it's Amell, and today we're going to solve valid mounting array. Given an array A of integers, return true if and only if it is a valid mounting array. Recall that A is a mounting array if and only if the length of A is greater than or equal to 3 and there exists some I with 0 is less than I less than eta length minus 1. So in this case, I has to be between 0 and eta length minus 1 such that a sub 0 is less than a sub 1 is less than dot 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 a sub I minus 1 less than a sub I. So it means that it is strictly increasing, as you can see in the picture, and then it reaches a peak. In this case, the peak is at position I, and after the peak it is strictly decreasing because a sub I is bigger than a sub I plus 1, greater than dot dot dot, greater than a sub eta length minus 1. So it has to be strictly increasing, it reaches a peak, and then it has to be strictly decreasing all the way to the end. So this is a valid mounting array. We have another example below. In this case, this is not a mounting array because, as you can see, this is not strictly increasing. So we are not allowed to have duplicates because in this case we are increasing, but then we find the 3 repeated. So this is not strictly increasing, so this is not a valid mounting array. This is not a mounting array. So this is an easy problem, and we can solve it in multiple ways. One way is to use 2 pointers. We can use I and j. Another way is to use 1 pointer, I, and another one ahead of it. So we're going to start with a solution, and then I'm going to show you a different way to write this problem. A different way to solve this problem. So one idea is that we scan from left to right and we go from left to right checking this condition. Initially it has to be strictly increasing. So we can have I, and also each time we check with the next element, the element at position I plus 1. And we check that this element at position I is less than the element at position I plus 1 each time. So we have to make sure that we get to a peak, and we have to make sure that it is strictly increasing. And after that, we have to use the same I, and we can go all the way to the end, and we have to make sure that it is strictly decreasing all the way to the end. So it's a very easy problem. We're going to start with this solution using I and I plus 1. So first, I'm going to have an integer n gets a value of a dot length, and I gets a value of 0. So while I plus 1 is less than the length of the array, and a sub I is less than a sub I plus 1, then I just keep incrementing I. So we start here, so we scan from left to right using I. We have to say I plus 1 is less than the length because we want to make sure that we're always within bounds. We're going to be comparing the element at position I with the element at position I plus 1, so we want to make sure that we're always within bounds within the array. So in this case, we keep moving as long as this element is less than the next element. So when we finish this iteration, there are a few possibilities. One possibility is that we made it all the way to the end. That means that the entire array is strictly increasing, so we have to return false because that's not a valid mounting array. Another possibility is that I never moved. So if I stays at position 0, that means that we don't have this uphill, right? We don't have, starting at position 0, we don't have the strictly increasing part that we're looking for. So in either case, we have to return false. So if I equals 0, or I made it all the way to the end of the array, we have to return false. Now, if we make it to a peak, then, for example, here we make it to this peak, then we have to continue checking all the way to the end because we want to make sure that after this peak, it is strictly decreasing. So that's what we have to do now. So we're going to say while I plus 1 is less than n, and a sub I is bigger than a sub I plus 1. plus plus I. So you can see that we continue from left to right, checking this condition because it has to be strictly decreasing. So from this peak, the remaining part has to be strictly decreasing. So at the end, if I was able to make it to the end of the array, then we know that this is a mountain array. So I'm going to submit my solution. Okay, so this is working perfectly. The time complexity is big O of n, where n is the length of the array, and the space complexity is big O of 1, because we're only using a few extra variables. Also, the length has to be bigger than or equal to 3, right? The length of the array has to be greater than or equal to 3. But this code handles those cases as well. So now, can I write this in a different way? Yes. There are multiple ways to write this code. So I can write a different algorithm. I'm going to show you now. So I'm going to reset the code. So now what we can do is that we can have a pointer here, I. This pointer is going to scan from left to right, looking for this uphill, for this strictly increasing part. And I'm going to have another pointer j starting at the end, and this is going to go from right to left, and it's going to look for the strictly decreasing part. So after I execute those loops, then I only have to check for 3 conditions, right? I has to be bigger than 0, j has to be less than the last position, and they both have to meet at the same peak. So this is another way to solve this problem. So I'm going to have integer n gets a value of a.length, I gets a value of 0, and j gets a value of n minus 1. So initially I'm going to check this part, so from left to right using I. So while I plus 1 is less than the length of the array, and a sub I is less than a sub I plus 1 plus plus I. Then I'm going to use j. I'm going to check for this part, the part that's supposed to be strictly decreasing. So while j is bigger than 0 and a sub j minus 1 is greater than a sub j minus minus j. So now I just need to make sure that I is bigger than 0, because I need to make sure that I was able to find this part starting from 0 that was strictly increasing. So return I is bigger than 0. Also, j has to be less than n minus 1. J has to be less than n minus 1 because I want to make sure that I was able to find a part that was strictly decreasing, ending at the end of the array. So end j is less than n minus 1, and also I need to make sure that I and j meet at the same point, at the same peak, because there could be multiple peaks, but there's supposed to be only one peak, and they have to meet at the same peak if these conditions were true. So end I equals j. If those 3 conditions hold, then I return true. So I'm going to run the code. Okay, submit the solution. Alright, so this is working perfectly. This is the same time complexity, big O of n, and the same space complexity, big O of 1. If you like this video, please press the like button, don't forget to subscribe, and see you next time.